Hello everyone, it's Benny, and welcome to part 6. Last time, we put the finishing touches on at least the core functionality in the ALU. So we can now take an 8-bit data into the ALU, do a whole bunch of arithmetic and logical processing on it, and when we're done, we can get it back out right here. The problem with this is we don't really have anywhere to get this data from, and we don't have anywhere to send it to when we're done with it. So today, we're going to take the first step into addressing this, and that is adding registers. Registers are going to be the primary source of data, both sending and receiving, in our computer. So yeah, it's basically memory, just designed to be pretty high performance because this is going to be using registers a whole bunch. So let's go ahead and let's get building. Okay, so a register is essentially just a memory cell, and the easiest way to do this is with repeater locking. So this will be our write command, and this will be whatever data we're trying to save. If I write and there's nothing, what do you know? The repeater stores nothing. If I write and there's power, the repeater stores the power. I can turn the data back off, and it remembers. And same thing the other way around. I can write a 0, back to nothing. The reason I'm going over this here is because I'm going to do this in a slightly different way. Instead of powering the repeater lock like this, I'm going to use our fan favorite, furnaces and comparators. The reason I'm doing it like this is because this will allow us to move the control wire right next to the lock itself. And this just lets us make it a little bit more compact. It lets us cram just a few more registers into a similar amount of space. So yeah. Now the only issue here is getting power into this repeater. Unfortunately, this requires a bit of creative busting. There's no way around using a repeater here, and we can use a block here otherwise. And this will be our input bus. So, data comes in this way, there's our data, and something to notice, the furnace only has power 1. So if you're using a hopper, for example, you can just put a single item in here. Doesn't matter. As long as the signal strength coming through the comparator is 1. So right now I have data on the bus. If I power this subtracts that signal from the comparator, and so the repeater is no longer locked. Turn it back off. Even though it doesn't animate it, this repeater is now locked. So I break this. See? Repeater's storing the power. I can do it again. And there, I've written a 0. So, cool. This is the basic way our register is going to work. The only thing now is, if I write a 1 again, we don't want to always be getting power from this particular memory cell. We might want to read from, say, a different memory cell. So, the way I'm going to do this is first I'm going to send this through a comparator. And it's not entirely obvious why I'm doing this, so I'm just going to leave it there for a moment, and you'll see in about 30 seconds why I'm doing this. So I'm going to go through a comparator, up 2 half slabs, and into a torch. And this is where our output is going to be. The reason I'm going to do this is because eventually I'm going to stack more on top of it. And you might notice if I have, for example, here, I'll just build one on top. See, power is leaking from this cell to what would be the cell above it. So this is why I have a comparator here. So I can subtract enough power from this that it only influences this torch and not the one above it. And that requires a signal strength of 12. So I'm going to place the furnace right here. You notice? Signal strength much weaker. And now, yeah, it does not reach the cell above it, no interference. So cool, this is the way we're going to do it. Oh yeah, and to control whether we're reading or not, we're going to power this. If this is on, then, well, we're not reading. If this is off, then we are. And this is our basic memory cell. And you might notice this is really painfully close to being too wide and tileable. But the cool thing is this can be too wide and staggerable. So we're just going to have to stagger it a little to get the next zone. We're going to do this by building one up. So I'm going to build the same thing again, except up by one. And there. And what I can do here is I can use a half slab and go up one. And that's so that these will still tile too high. And there. And I can go here with another comparator in subtract mode. This comparator does not have to be in subtract mode, but this one does. And yeah, so now this one has to have power of 12. This one has to have power 1. So be careful about your signal strength here. If you get the signal strengths wrong, then this unfortunately will not work. So yeah, other than that, same sort of concept. Just bust down. Well, I'm busting down just so this will tile better, but yeah. And this, yeah, that's a slight problem. An easy way to fix this, put a block on top of this torch, and there. Now, the torches are both powering this wire. No fancy staggering needed. And there you go. This is now... Oh, I forgot this control wire. But again, same concept, not too difficult. There. So now we have a memory cell that is too wide, staggerable. And these furnaces would be where these snow blocks are. So in fact, let me just replace those. I'm going to break this comparator, replace this. This will need to be 1, and this will need to be the 12 furnace. Now I need the repeater for the memory, and the comparator in subtract mode for the output. And cool, this is the basic design of our register system. Okay, so now we have two memory cells that can stagger next to each other, but this isn't a complete register system yet. So I'm going to stack this up a few times. I'm going to set, I think, this to position 1. Cool. And now I'm going to fly under here, right here, sure. Set that to position 2. And right where this block is, I'm going to copy. If I go up 1, I should be able to paste -A so that air doesn't overwrite everything. And cool, this should have another pair of memory cells on top of it without interfering with anything. And it appears that that is the case. So awesome. So let's get 8 of these because we have 8 bits to store. So that's 3, 4, 5, 6, 7, 8. Okay, cool. So now we just need to finish up doing the write command and the read command. And this really just means making sure we can power all the way to the top. So I'm going to replace this block in the write command with wire, and I'm going to put a lever here. If I power the lever, I'm now writing to all the memory cells, and it reaches all the way to the top. Awesome. I can do the same thing over here, and just put, yeah, make sure you have redstone dust there, and the lever. So awesome, now we have a write command here. Should be able to go all the way to the top. Excellent. So now we just need to do the same thing for the read command. So I'm going to put a block here, and I'm also going to change this to a block, and I don't think this is going to reach unless I put a torch here, but let's see. I'm going to put a torch here, going to draw up a lever there to control it. The reason I'm doing the torch is because this is inverted. When power to this is on, then we're not reading. And yeah, look at that, just barely reaches the top. So this is the right signal strength. Actually, I can go ahead and break that. So again, break the half slabs, replace them with solid blocks, and change this, or add a torch. And now we have our 2 read commands completed. So let's go ahead and just do some basic test inputs while we're here. So I'm going to input, sure, I'm just going to set up a basic 4-bit input system, and I'm going to save, actually let's change it up a bit. Let's save 7, save that to this cell, and let's save 2 to this cell. And now if I read right here, you notice it's inverted, but we are indeed reading a 2. Just, well, the whole thing is inverted. And over here we should read an inverted 7. Awesome. So, there we go. We have 2 8-bit memory cells, and they both appear to be in working order. So at this point, what I should be able to do is set this to position 1, and this to position 2. Wait, not this, excuse me, I need to go down. So this is position 2. Actually, I should make sure position 1 captures everything, so I'm just going to go ahead and go up 1 and set this to position 1. And what I should be able to do is I should be able to stack 1 and still have everything work. So right now, I think this actually should have stacked the data because I didn't overwrite anything. So if I read here, that reads the 2. Cool. And if I read here, I think the server's lagging. That's okay. Read here, that reads the 7. And I have been kicked from the server. Okay. Okay. I am back. And everything appears to be where I left off, so stacking seems to have worked here. And if so let's just test over here. I'm going to write all zeros, one final test before we finish stacking. Write all zeros, read all ones. Perfect. So I'm going to just, actually I think I lost my selection here. So you already saw me do that, so I'm just going to go ahead and reselect it off screen. One moment. Okay, so now I should be able to stack 3, and this should give us 8 memory cells total, which is great. Except, we don't actually need 8 memory cells, we just need 7. At least in the design I'm going for. So, I'm going to set this to position 1, and this way down here, somewhere, to position 2. I'm just going to set 0. We don't need it. We need 7 memory cells. And that should just about do it. So this is our register system, at least the core parts of it. We're still going to need a slightly easier way of reading and writing to the different cells eventually, but that's okay. That can come later. For now, we have the memory system. And, yeah, all we have to do now is take this and connect it to the ALU. Hello, it's Future Benny. And I have just noticed I made a pretty silly mistake. These comparators right here have absolutely nothing power in them. And that's not what we want. So I'm going to go here position 1, and this is position 2, and I'm going to expand 1. So now what I can do is I can copy, and right here I can paste. So cool, just like that, we now have these in the correct positions. I can just go ahead and do this for all of them. And yeah, just make sure you have that, because otherwise the final bit of your registers will not work, and it won't be how you like it. So, I went ahead and did a fair bit of testing off-screen, and I think I know the perfect way to hook this up to our ALU. The only thing is I might have modified some of the busing slightly in the ALU, but it should be pretty close to how it was before in any case. So hopefully that's not too confusing. In any case, let's go ahead and select this. So I'm going to set this as position 1, and I'm going to fly over here and set this down here as position 2. That's Great, I'm pretty sure that selects everything. So now right here, this is where I'm going to copy. Now, the register system, if you remember, whatever you input, it inverts it when you read it back out. So if I save a 0, I'm going to read out a 1. If I save a 1, I'm going to read out a 0. So what I'm going to do is I'm going to invert the ALU output. That way, when the register inverts it, the end result should be the same as the original ALU output. And there. So right here, I'm now going to paste. And this should fit pretty closely to our ALU. But actually, no, I don't think I can get this any closer without screwing up some of the logic. So I think this is just about as close as the registers can get to the ALU. And there, so I'm going to go ahead and break all these lamps. We don't really need them anymore. I'm going to place all the torches. And I'm just going to do this by hand because I think it's quick and easy enough. Awesome. So now we have all the inputs, we have the register input handled. Now we need the output to go into the ALU input. And this is a slight problem because we have several different torches, each of which will produce a slightly different signal strength right here, and we need a very precise signal strength coming into the ALU, or this ALU is not going to work. So what I'm going to do, I'm going to put a repeater right here. So this way, no matter what signal strength I get from whatever torch, right here, it's going to be full strength. And now I'm going to put a comparator in subtract mode, and that should just about give us the correct signal strength. And what I can do is I can fit a comparator right here. Yeah, and I can put a furnace right about here. Whoops, hang on. Right here. And this should give us exactly the right signal strength for everything to go through. I'm going to test this by sending data through. So if I send data through, yeah, you can tell it's right because this is just barely reaching here. If I put redstone on top of this torch, it doesn't power anymore. So this is precisely the correct signal strength. So I'm going to go ahead and turn that off. And great! The only other thing is I'm actually going to turn this repeater into a repeater lock. This way we could save whatever input is coming in to the ALU. And that way we can do whatever you want with the registers and it won't interfere with what the ALU is doing. So, there. We won't need this right away, of course, but this is a good thing to have. I can go ahead and break this torch now, and I think I can start trying to stack this. So I'm going to set this as position 1, this is position 2, and I'm going to expand 2 and expand 1 down. It should be enough to capture everything, except for that half slab, but we'll deal with that in a moment. So now I should be able to stack 7 down. I don't know if I mentioned this, but make sure the furnace signal strength 6. That's precisely the right amount. Or hopper, or whatever else you use. But yeah, now we should have, good, all our furnaces appear to be the right signal strengths. And this appears to just about be putting everything in the right position. So I'm going to go ahead and put half slabs all the way up. That's right. Whoops. And now I can just add redstone all the way down. And cool. Now we should, keyword should, have everything set up and working. We just need, well, we do need to be able to write to this, so I'm going to have a torch here, or not torch, a lever here. So this should reach everything. And awesome, now we can save whatever our second input is to the ALU, and then we can do whatever we want with the registers, and it won't bother what the ALU is doing. And that's cool. This way we can read, say, something to the register and send it to memory or something. It's just, again, it's nice to have. And this should be everything we need to do to hook the registers up to the ALU. So that is everything I wanted to cover in this video. And in fact, we have most of a working computer already. In fact, I just went ahead and ran a Fibonacci sequence program manually using all those different switches we have laying around. And it worked just fine. And it was kind of cool to do so. So yeah, just wanted to point out that we are making progress. We're pretty close to having something working. And yeah, thank you. Hope you enjoyed. Hope you learned. And next time, we're going to start doing something about these, just this enormous number of different levers and such laying around. Because it's kind of gotten a little bit ridiculous at this point. There needs to be a better way to control everything in our soon-to-be computer. Thank you. Hope you enjoyed. Hope you learned. And I'll see you then.